Lagrange actually first proved this, and then Gauss went much further. The orbits of SL2Z on the set of primitive binary quadratic forms of discriminant D are finite. And even better than that, they have a structure, we're not going to do this, of a finite abelian group. Namely, you can multiply two orbits and get another orbit in some way. That's called Gauss composition. And this turns out to be, this finite abelian group under Gauss composition turns out to be the same finite abelian group that we would call the Picard group of the ring of discriminant, a quadratic ring of discriminant D. You can put it like that, AD, where AD is by definition Z plus Z, D plus root D over 2. So it's the group of projective modules of rank 1 under tensor product for that ring. That's an amazing, amazing result. Gauss didn't have rings and modules, but he had this orbits on binary quadratic forms, and the orbits formed a finite set, and on that finite set he defined a group multiplication. And that's going to be his replacement for ideals and ideal classes, etc. Now, we're particularly interested in the case where D is the discriminant of a quadratic field. So remember, what that means is that D is congruent to 0 or 1 mod 4, and is square free as possible. So in that case, you don't have to worry about this primitive condition. Any binary quadratic form with this kind of discriminant is automatically primitive. But Gauss worked with all the different discriminants, and so this ring is this ring is the ring of integers when D is of that form. If D is square free as possible, this is equal to the ring of integers in my imaginary quadratic field. Otherwise, it's an order of some finite index of the ring of integers. But it works in all the cases. Okay, so how did he prove that the set of primary, and how do you enumerate the orbits? Well, he used Lagrange's theory of finding a reduced representative. So it turns out that in every orbit of SL2Z, Lagrange had done this for GL2Z, there is a unique reduced form. And reduced means that B is between minus A and A, which itself is less than C. A and C, remember, are both positive. So B can be positive or negative, but it's bounded between minus A and A, or you can have equality. So B can, if B is positive, it can be equal to A, which itself can be equal to C. Well, if you're able to manipulate a given binary form by changing coordinates by SL2Z to make its coefficients lie in this region, and we saw that region for tau was the usual fundamental domain for SL2Z on the upper half plane, where the real part goes between minus a half and a half, and the imaginary part is greater than 1. So you can either think about the orbits of SL2Z on the upper half plane, or you can think of them just on binary forms. Okay, suppose you have these conditions, and I claim the proof that the number of orbits is finite is clear, because you have this 4AC minus B squared. That's a positive number, B. It's minus B, actually. It's a positive number, right? Because the discriminant is B squared minus 4AC is a negative number. So that's fixed. This is a fixed number. You're counting the orbits of discriminant B. All right, but if you see, if the form form is reduced, C is bigger than A, or bigger than or equal to. So this number is bigger than or equal to 4A squared minus B squared. Right, because C is bigger than A for the, but on the other hand, A is an absolute value bigger than B. So A squared is bigger than B squared. So this number is bigger than or equal to 3A squared. And you see, this D is fixed, so that tells you there are only finitely many possibilities for A, because 3A squared has to be less than minus D. And once you bounded A, then this tells you that there are only finitely many possibilities for B. So this bounds A. Then you get a bound on B. And then finally, since you know what this is, there are only finitely many possibilities. Once you got A and B bounded, there are only finitely many possibilities for C. So once you fix the discriminant and you know that your form is reduced, you can actually count the forms out that have that discriminant which are reduced, and that gives you the number of orbits. And this is extremely efficient way of calculating the class groups, or at least the class number of imaginary quadratic fields. In fact, it's the best way to do it. So for example, if I take a case where the class number is non-trivial, one of the first famous cases, which was discovered by Kummer, discriminant minus 23. Well, if you look at this, this says that 23 is bigger than 3A squared. Okay? So that says that A has to be less than 3. So A has to be either 1 or 2, right? Because it's a positive integer, less than 3, okay? And if A is 1, then you see the possibilities for B, well, it's either 0 or 1, and you have to be able to solve for C. So you get the form 1, 1, 6. I hope that's right. 1 minus 24 is 23, right? So B has to be equal to 1. B can't be 0, because if B were 0, you have 4AC is equal to 23, which can't be the case. So B is 1. And then if A is equal to 2, well, that gives a little bit more room for B. You see, B can be between 2 and minus 2. Again, it can't be even, because then this number would be even, which it isn't. So B has to be odd, so it could be 1 or minus 1. And if B is 1, you get the form this, and if B is equal to 1, and if B is equal to minus 1, then you get the form 2 minus 1, 3. And that's it. That's the only thing you can, that's the only forms, reduced forms of discriminant minus 23 you can get. So in this case, there are 3 orbits of SL2Z. And it turns out that these two are equivalent under GL2Z, because if you take the element 1 minus 1 in GL2Z, so you're taking x to x and y to minus y, then that changes the sign of the xy term. So in Lagrange's calculation, there would be 2 orbits of GL2Z, but it turns out it's better to use this orbits of SL2Z, because that's what gives you the finite abelian group. We're going to see that these orbits give the class group of this ring is Z mod 3. And if you identify these 2 orbits, that's identifying the 2 non-trivial classes in this group. And so if you do the GL2Z orbits on the set of binary quadratic forms, you get this class group up to inversion. So then you get this, and if you do GL2Z orbits, they correspond to the class group modulo inversion. And since in a group of order 3, you have 2 non-trivial classes which are inverses of each other, you get that. Okay, so Gauss, in fact, made extensive tables of these binary quadratic forms of a given discriminant once he had this theorem of the orbits being finite. He just enumerated them the way we did. And he studied the growth of these, of the number of orbits. Let's leave this up here.
Can I ask a question?
Sure, go on.
So like, the curve group of the integers, can you think of it as a, I guess you can think of it as the line models on the curve. Does it suggest that you can get the line models of the curve as some quotient of the group by something bigger, maybe a moduli of the project forms or something like that?
Well, I mean, in all cases, they can think of them as line bundles. They just become line bundles on a singular curve. I mean, when this thing is not the maximal order, it's the singular curve. But I mean, it's isomorphism classes of projective modules. I mean, you can just take all projective modules, but then that's too big.
Yeah, but can you think of it as like geometrically as a quotient space or some other thing? So you're modding by geometry as of Tuesday, so.
No, I don't think so. I mean, at least I don't know. So in any case, Gauss made tables of these things, and he made a guess as to how the class number grows with the discriminant. So Gauss's guess, as minus d goes to infinity, the number of classes, which he called h of minus d, behaves like the absolute value of d to the 1/2 power. We'll come back and see what that means for the class number formula later. So it grows at essentially the same rate as the square root of the discriminant. So more precisely, he guessed that there were two constants, so that h of minus d was less than a constant times the absolute value of the discriminant to 1/2 to the log d, and greater than another constant times the discriminant to the 1/2 divided by the log of the absolute value of d. And that's still unknown. That's a fundamental question which nobody knows the answer to. So, in particular, in saying that it behaves like this says that for any fixed number, any fixed integer, there should be only finitely many discriminants which have that class number. So only finitely many discriminants have class number 1, or principal ideal domains. Only finitely many have class number 2. Only finitely. That much is known, but this precise growth is not known. So Gauss was able to prove something. He proved, and this is the first result in the geometry of numbers, which we're going to get into when we do, and Dirichlet followed his ideas. He proved that if you summed over all the discriminants less than x of h of minus d, well then if it behaved like this, you'd be summing essentially the square, the discriminant, the d to the 1/2 power. And when you integrate x to the 1/2, you get x to the 3/2. So you'd expect something like x to the 3/2, and Gauss could prove that it was pi over 18 times x to the 3/2 power. So he proved an average result on the growth of the class number, even though he couldn't prove it for an individual class number. How did he do that? Well, as I say, that's geometry of numbers. And he said, look, if I sum over all the different discriminants, where the class number, then if you think of each element in the class group being represented by a reduced form, this is essentially the number of points x, y, z with integer coordinates, and the coordinates would of course be a, b, c, in the region of R3, defined by the reduced equalities, namely the region, let's call it A of t, where minus x is less than or equal to y, is less than or equal to x, is less than or equal to z, and 0 is 4xz minus y squared is less than t. So this says we're a reduced form. I mean, these are special cases of that, which are on the boundary, and I put the boundary in. And this says that we're going from all negative discriminants from 1 to up to t. And so I get this many things, right? I mean, modulo a little bit of worry about the boundary and things like that. And then Gauss calculated the volume of this region. It's not compact, but it has finite volume. It's pi over 18 times t. That's a nice t to the 3f, sorry. And so the number of integral points you'd expect in a reasonable region of finite volume is about the volume of the region, because, right, each integral point is like in 2 space, it's in a fundamental domain, volume 1. And so this way of counting integer points by calculating volumes of regions and estimating them by the volume of the region is the beginning of the geometry of numbers, which is what Dirichlet is going to use to prove this estimate. This, by the way, would be another really nice topic for the paper. The growth of the class numbers of imaginary quadratic fields. So it's still a very interesting open question. And you can start with Gauss's average calculation, and then a huge amount of work in the 19th and early 20th century on trying to get this estimate. Okay. All right, so let's go back to what Dirichlet was proving and reinterpret ideals and their classes, etc., in terms of binary quadratic forms. And that's why, as I said, Gauss actually had the ideal class theory of imaginary quadratic fields when he wrote down the theory of binary forms without people knowing what an ideal was or anything like that. So suppose I have this imaginary quadratic field, and let I be a fractional ideal of the ring of integers in the class of C inverse. It turns out you have to go from inverses, etc. So if we have the theory of ideals and we have ideal classes, we can take an ideal which is in the class of C inverse. It's not integral or anything like that. All right, and let gamma be an element in this ideal. Well then, what does that mean? It's contained in the ideal. That means if I multiply it by anything in the ring, that's contained in the ideal. So it says that the principal ideal of gamma is contained in I. Okay? Well, if it's contained in I, then if you use division of ideals, fractional ideals form a group. And so if we take J and we define that to be the ideal gamma A divided by the ideal I, that's an integral ideal. In the class of C, because this is a principal ideal, that's in the trivial class, and we've divided by an ideal in the class of C, so we end up in the class group going from C inverse to C. Okay? And if I took a different gamma in I, if gamma prime is in I, then J prime, which is gamma prime A over I, is in the same class as J. So as we run through elements of our ideal, we're producing integral ideals in the same class as C. And if you think about it, this gives a bijection. And that's what we're going to use. Between elements, well, almost a bijection. elements gamma in I up to multiplication by A star, which is, remember, in this case, a finite group cyclic of order W, and W is either 2, 4, or 6, usually 2. It's in bijection with integral ideals J of A in the class of C. So that's what we need to work with, right? We need to work with ideals in the class of C, and we're going to calculate their norms. But we can now identify every integral ideal in the class of C if we had an integral ideal in the class of C, then the way we get gamma is we multiply J by I. That's a principal ideal because I was in the class of C inverse. It has some generator, gamma. Gamma lies in I because J was an integral ideal and is well defined up to a unit, namely a generator of an ideal, if its principal is well defined up to a unit. Good? So we get that bijection. All right, now, how do we get the binary forms? Well, take this ideal, let's write these elements gamma in I as X alpha plus Y beta, where I, as a free Z module, is generated by alpha and beta. I mean, whatever it is, it's a Z module which is free of rank 2. So we can write it like that. All right, and then the norm of gamma is a quadratic form in X and Y. And in fact, if I take the norm of the ideal J, this integral ideal, that has to be an integer, which is equal to the norm of J was the ideal, here we are. So J is the ideal gamma A over I. The norm of J is the norm of gamma divided by I. And I divides the norm of gamma because this is contained in I. So this is the norm of this ideal, which is the norm of gamma, is divisible by I. So this is the binary form. Where A, B, and C are integers because it takes integral values. J is an integral ideal. And moreover, one finds that B squared minus 4AC is D. So that's a computation one has to do. So you get so from every integral ideal of A in the class of C, we get a binary quadratic form of discriminant D by associating to that integral ideal an element gamma in I up to multiplication by blah, blah, blah. And this norm doesn't depend on multiplication by a root of unity because the norm of any root of unity is 1. So this is a binary form. It turns out to be primitive, binary form. And when you change the different, right, good. And it turns out to, and the orbit is independent of the choice of gamma, because if I chose a different gamma, I would just, I'd have a different expression for, if I took a gamma prime, I'd write it as X prime and Y prime, and I'd get a different binary form in terms of this, but it would be in the same class. Dependent gamma, and the class of the orbit can be identified with the class C. And in particular, we can rewrite this partial zeta function that we had in terms of these binary forms, because the binary form is what's giving the norm of the ideal, and that's what we need in the partial zeta function. So this partial zeta function in the class C can be written in the following way. It's 1 over W, the sum over xy not equal to 0, 0. That gives the non-trivial elements of 1 over ax squared plus bxy plus cy squared to the s power. Where you pick a binary form in the class of C, and it gives the norms of all the ideals, because it gives the norms of gamma for every element gamma in I. Okay, for different values of x and y. I mean, if I took another element, gamma prime, it would be x prime, different value of x, a different value of y, different value of this form. And so that's what Dirichlet worked with. These were the series that Dirichlet studied. He didn't have ideals, he didn't have ideal classes, but he had orbits on the space of binary forms. And so if we did it in this case over here, what would the zeta function look like for him? Well, we have the 3 orbits. So the zeta function of q squared to minus 23 s for Dirichlet would be, well, it's a 1/2 the sum over the principal class of 1 over x squared plus xy plus 6y squared to the s, plus 1/2 the sum over this class, which would be 1 over 2x squared plus xy plus 3y squared to the s, and plus 1/2 the sum over this class. Okay? All incredibly explicit once you have those binary forms. So you might think, oh, well, this ideals look great, but you have to parameterize the ideals, and you have to know what their norms are. And by this theory of binary quadratic forms, you can see what the norms are of the integral ideals. They're the values of this binary quadratic form. Cool? And as I say, to get the binary quadratic form, I had to choose this basis of the ideal, and if I change basis in an oriented way, I get an equivalent binary form. Okay, so what did Dirichlet prove? He proved okay. So notice that I have a 1 over W in all these series, right? So if I just study this, I want to prove that its residue at s equal 1 is equal to this, but I don't have to worry about the W anymore. So just 2 pi over the square root of the absolute value of d. For every binary form, if you just study this series, it has a pole at s equal 1, and you have to prove that this is its residue, where d is the discriminant of the binary form. So now it's, it's completely explicit. How do you do that? Okay. So he's going to calculate how many values of that form. Right. Let's see if I can get this properly. Okay. So the equivalent formulation is i.e. the number of elements gamma in this ideal in the class of C inverse, but it turns out not to matter what the class it is. That's the big thing. Where it's such that the norm of gamma is less than x times the norm of I, because remember, the norm of the ideal is the norm of gamma divided by I. This is the norm of I apologize. So the value of this thing is less than x. So that should behave like 2 pi over the square root of the absolute value of d times x, plus an error term, which is gonna be about x to the 1 half. As I say, he did it with the binary forms, but that's what we're now after. Okay. As I say, see, now you're just counting elements in a lattice. This ideal is a lattice. So for example, suppose the ideal were the full ring of integers. Why not do it in the trivial class? Let's see what it looks like in the trivial class. All right, what is the ring of integers? Well, we know that it has a basis, c plus e, d plus root d over 2. We worked out the ring of integers. So the generators for this is a z module. You have this element 1, 0. And let's suppose d is odd. You have another element up here. D plus root d over 2. And they span a little parallelogram. So that's the fundamental domain for translation in the complex numbers by elements in the ring of integers. And that fundamental domain, I claim, has volume equal to the square root of the absolute value of d over 2. Well, that's the calculation of a determinant, right? I mean, you have to, this is 0.1, the complex number, so it's the determinant of the matrix 1, 0, and the real part of this is d over 2, and the square root of d over 2, and when you calculate that determinant, you get this. So basically, you're going to get one element in the ring of integers every time you have a piece of volume that's about this large. That's the basic principle. Right? If we're counting the number of elements, number of gamma in A, with gamma bar less than x, because that's what, it is less than x times the norm of I, then we're counting the number of elements in the ring of integers which lie inside of a circle of radius the square root of x times the norm of I. And the number of elements you'd expect to find in that, well, this is the case for the full ring of integers, but the norm of the full ring of integers is 1, so just let's let the square root of x, okay? Well, the number of gamma in A expected would be the ratio of the volumes. Area of the circle divided by the area of the fundamental domain. Because you get basically one element in the ring of integers for every piece of area of the fundamental domain. Well, the circle of radius x has area pi capital X. You divide by the volume of the fundamental domain, right, which is square root of d over 2, right? And you get 2 pi over square root of absolute value of d times x. Of course, there's an error term about the points on the boundary of the circle, but that's about the size of the circumference, which is the square root of x. And if we didn't do this for A, but we did it for I, the volume of the fundamental domain is square root of absolute value of d over 2 times the norm of I. Because I, the norm of I is the index of I in A. And once you have a fundamental domain for A, you take a subgroup of A, the volume of the fundamental domain is multiplied by the index. And likewise, the area of the circle of radius x times the norm of I would be pi times the norm of I. So this would be norm of I. Here we have another norm of I. They cancel out, and you get the same answer. And that was Dirichlet's calculation. Of course, there's a lot of justification, but the miracle I think that he discovered and what makes the class number formula work is that you get the same count for all the different ideal classes. So that whatever the residue of this thing is, it's somehow independent of the class of this binary quadratic form. Different zeta functions are completely different. I mean, this is a different function than this as a function of s, but as s tends towards 1, they have the same order pole. All right, now, that would be pretty good if Dirichlet had stopped there, but he didn't, because he had two different expressions now for the zeta function of a quadratic field. I should say he did the real case too, and in the real case, when you compare elements in an ideal to ideals in the inverse class, you have to worry about the unit group, and that's where the regulator comes in. Okay. Now, I'm going to introduce you to Dirichlet's greatest contribution, because all this was just prelude. So he said, well, look, I have two different decompositions of the zeta function of a quadratic field. The first was the additive decomposition that I used to obtain the class number formula. Okay, with D, I have zeta of S is the sum over the different classes C of zeta sub C of S. That was a naive decomposition. But I also have it written as the product of the Riemann zeta function times the L function of a character of the integers mod D star. And that decomposition was reflecting the law of quadratic reciprocity. So this gave me a formula for the residue. So we've seen that the residue at s equal 1, at least in the imaginary quadratic case, is 2 pi over the absolute value of D times h over w. The residue of this function we saw is 1, so this is equal to the value of L chi 1. And that was his proof that this value is non-zero, because all these terms are non-zero. But he then proceeded to find an analytic expression for this. I mean, this is the sum of A prime to D of chi of A, which is plus or minus 1, over A to the S. Over A. It's a conditionally convergent sum. Conditionally convergent sum. And Dirichlet did an analysis of this sum and found an analytic formula for it. And the analytic formula is the following, if I got it right, and I'm going to prove this for you next time. It's equal to minus pi over the square root of the absolute value of D, that was amusing that all that turned up, times the sum from B is equal to 1 to D. And it's important that you sum from 1 to D and prime to D. So it's really only going up to D minus 1. Of chi of B, you evaluate, that's a plus or minus sign, and then you multiply it by the rational number B over D. That's not a quadratic symbol or anything, it's just a rational number between 0 and 1. All right, so we just took this problem to find a value of this convergent sum. Notice that this is now a finite sum. It depends on what the discriminant is. Okay, now that's surprisingly similar to this. For example, this cancels, the pi cancels, and so you basically get that 2h over w is minus this thing. And since w is almost always 2, we get a formula that h is equal to minus the sum of chi of b over d, which is a completely explicit formula for the class number. I mean, it may not be the easiest thing to calculate as the discriminant goes up. B is equal to 1 to d. And this, there are many, many different things called Dirichlet's class number formula, but this is the ultimate result of it. And you prove it in two ways. You take this decomposition to get the formula for the residue. Then you take this decomposition and you work out the value of this L function at 1 as a finite sum. And so this was a amazing achievement at the time. Let's see if we can do it. Let's see if we can check it for this case. So this case is h is 3, right? Okay. So this function chi mod 23 is just a quadratic residue symbol, so we can write it. And so h is supposed to be equal to minus the sum from b is equal to 1 to 23 of the quadratic symbol b23 times the rational number b over 23. See the advantage of different symbols? Pretty cool. Okay, how do we do, so what is that? That's equal to the sum of the quadratic residues between 1 and 23 of b minus the sum of the non-residues between 1 and 23, b, all divided by 23. And then you have to take minus it. Well, let's see if we get the right answer. So we need to know the quadratic residues mod 23 and what are the non-residues. And you'll see how powerful this was. If it works out. If it doesn't work out, I did. All right, so quadratic residues. Well, 1 is always a quadratic residue. Now, 2 is a quadratic residue, and I think 3 is also a quadratic residue, mod 23. You guys can check me out. All right, let's try it. 323. Well, they're both congruent to 3 mod 4, so it's minus 23, 3, which is minus 2, 3, which is 1. Okay. So 2 is a quadratic residue, 3 is a quadratic residue. That means that 6 is a quadratic residue. 4 is clearly a quadratic residue. 6 is a quadratic residue. 9 is a quadratic residue. 16 is certainly a quadratic residue. How many quadratic residues do I need? 11, right? I mean, they're half of them. 1, 2, 3, 4, 5, 7. I'm going to need more. 5 is not a residue. 7, 3, 23, 7. That's good. 7 is a quadratic residue. So I need a 7. 7, 9. Since 7 and 2 are residues, so is 14. So is 16. And 21 must be a residue. 3 and 7. And I hope that's it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Uh-oh, they're missing 1.
13.
13.
Yeah.
Good, 13, thank you. Okay, now we're set, because the non-residues are everything not on this list. Let's make sure we got enough. So 5, 6, 7, 8, 10, 11, 12, 15, 17, 18, 19, 20, and 22. 1, 2, 3, 4, 5, 6, 7, 8, 9, 11. Now notice that the quadratic residues occur more in the second half of the interval than the first. That has to be the case by this formula, because if you take quadratic residues minus non-residues, you better get a non-negative number, because minus it is going to be related to the class number. So a corollary of this ridiculous formula is that there are more quadratic residues in the first half of the interval and more non-residues in the second half of the interval. All right, but we still have to do it. So we have to add these up, and then add these up. Well, that we could do once we do the first adding up. All right, here we go. 6, 10, 16. This is what you get for playing a lot of golf. 16, 23, right? 23. And 9 is 32, 45, 59. This is getting much harder. 59, 75, right? 96. Is that divisible by 13? 96. Uh-oh. Did I do that right?
7 is not a quadratic.
Oh my God, I screwed up. It's not a residue, really? Oh geez, let me try it again. All right. 720. Minus 23. Oh God, you're absolutely right. This is all wrong. Oh, this is all wrong. 14 can't be a residue. All right, go do it. You know, I'll tell you a great story that I like very much about trying to do this crap at the blackboard. So go do it and verify that this minus this divided by 23 is minus 3. That's incredible. All right, so here's the story. So a very famous discovery in late 20th century number theory was the fact that elliptic curves were related to modular forms of weight 2. People have all kinds of trouble with the naming of this. Some people attribute it to Taniyama, but Taniyama had only the vaguest idea of it, and then other people attribute it to Shimura, but there's not a single sentence in Shimura's entire opus that states this conjecture. But I like to attribute it to Andre Weil, who made it extremely precise and said that, well, if you had an elliptic curve of conductor N, there should be a modular form of weight 2 and level N. That's something that's falsifiable. Okay? And when he was lecturing on this in Paris, he said, you see, there are no elliptic curves known of conductor less than 11, and that's the first place you get a modular form of weight 2, so that's a piece of evidence that there's this modular form of weight 2 and conductor 11, level 11, and there is an elliptic curve of conductor 11, so everything's good. So at that point, my thesis advisor, John Tate, was in the audience, and he said, actually, I have 2 different elliptic curves of conductor 11. You only have one modular form. So Weil said, well, it's obvious your 2 curves are isogynous. I mean, I'm only parameterizing isogeny classes of elliptic curves, non-elliptic curves, and here, your 2 elliptic curves must be isogynous and related to this one modular form. So Tate said, well, how do you know that? How do you know that? And Weil is getting more and more exasperated. He says, you kids, you don't know how to compute an isogeny, you don't know how to do anything, anymore. What the hell do you know about these elliptic curves? So Tate said, well, this one has a point of order 5. And Weil said, well, that's it. You just divide out by that point of order 5 and you'll get the other elliptic curve, and then they'll be isogynous, you see. And Tate said, well, how do you do that? Weil's like, you kids, you don't know anything. Give me the equation of the curve. He writes the equation of the curve on the board. What's the name? What's the coordinate of the point of order 5? He writes that down. And what you have to do in that case is you have to study the automorphism of the function field where you translate by that point of order 5, and you have to calculate the invariant function field. And that's the equation of the isogynous curve. Well, that's not so easy to do, even for an isogeny of degree 2. An isogeny of degree 5, it's frightening. But anyhow, they just launched into this computation, and everybody in Paris was just sitting there going, oh my God, this is unbelievable. And of course, he got tripped up. Like I did. 7 is not a quadratic residue. All right. And after about a half an hour, the thing was just grinding to a halt. He wasn't getting anywhere, and he sort of threw down the chalk and stormed out of the room. And the story ends is Tate tells me that a week later, he was sitting in his Paris apartment working away, and the telephone rings, and he picks up the phone, and on the other side is Weil, who doesn't introduce himself. He just says, they're isogynous, and hangs up. So it's just a general principle that you should do these computations outside of class. So I'll see you next week, and we'll prove this wonderful formula. And that'll try to get us into the machinery that we need to do the functional equation to. Okay, you guys check that the class number is 3. There was a very good talk today, by the way, about the geometry of numbers. If you're interested, a good speaker, Wei Ho, in the number theory seminar. He's giving a free talk.
Yeah, 1 second. What do you compose in Dirac?
Pardon?
What do you compose in Dirac with this formula of general number?
Is there an analog of this explicit formula? No. No. Just for abelian fields.
I see.
That's again something we very much like to know. Okay? Yeah, I'm going to do the job.